Our last few lessons we've been working on factoring polynomial expressions. And to review our factoring process, we said we always look for the greatest common factor that we could divide out from every single term. In this case, it's 1. Then we think of our number pattern, taking the leading coefficient times the constant. So 1 times negative 30. What times what gives us negative 30? And then what plus what adds to give you that linear term of negative 7. We know that we could use a negative 10 and a 3 to make that happen. So we can write it as 4 terms. And we typically like writing the polynomials with 4 terms because we can look at it in pairs and divide out what they have in common. So this first pair here, we could divide out an x. The second pair, we could divide out a 3. We'd be left with x times x minus 10 plus 3 times x minus 10. Again, the goal is to make sure that they're multiplied by that same factor. They're being multiplied by x minus 10, so we can write it as factors of x minus 10 times x plus 3. We're going to try factoring some other trinomials using the same methods. For looking at our first one here again, look to see, does it have a greatest common factor? If so, divide that out. Then see if you can use your product sum method to find the factors. As we can see with number 1, there is no greatest common factor other than 1 to divide out, so then we can think about our number patterns. What times what gives us 20, and what plus what gives us 12. We know 10 and 2 will multiply together, get 20, and add to give us the 12. So again, we could write it with the 4 terms, and looking at and splitting into pairs and dividing out the common factor from each pair. Our first pair we could divide out a y, the second pair we could divide out a 10. So we have y times y plus 2 plus 10 times y plus 2. Y plus 2 is being multiplied by y and 10, so here are our 2 factors. Our second polynomial, z squared plus 13z plus 30. Again, looking for a greatest common factor, we can see we only have a 1, so we'll continue to the next step, thinking what times what gives us 30 and what plus what gives us 13. We know 10 and 3 would meet both of those requirements, so again, we could write it as 4 terms, look at into pairs, and divide out what they have in common. The first pair we could divide out a z, the second pair we could divide out a 3. Again, this point we want to see, are they being multiplied by the same factor? They are, z plus 10, which is being multiplied by z and 3. Let's see if we can factor these 2 trinomials. Again, for number 3, look to see if it has a greatest common factor. And right now that's 1, so then we'll go to the second step, thinking about what times what gives us negative 12 and what plus what gives us 1. We know a 4 and a negative 3 would accomplish both of those goals. So we can write our polynomial with 4 terms, think of it in pairs, and divide out what they have in common. The first pair we could divide out an x, the second pair we could divide out a negative 3. Again, we can see that both of the pairs are being multiplied by that common factor of x plus 4, so we can write it in factored form of x plus 4 times x minus 3. Our fourth polynomial, again looking to see if it has a greatest common factor. It does not, it just has a 1, so go to the next step, thinking what times what gives us negative 16, and what plus what gives us negative 6. We can use a negative 8 and a positive 2 to accomplish that goal. So again, we could write it as 4 terms, look at it in pairs, and divide out what they have in common. The first pair we could divide out an a from each term, the second pair we could divide out a 2 from each term. So we'd have a times a minus 8 plus 2 times a minus 8. Both of them are being multiplied by a minus 8, so that common factor, which was meaning that the other factor has to be a plus 2. So let's try factoring these trinomials. Again, we look to see, does it have a greatest common factor to divide out? And it does not, besides 1, so we'll leave it as it is. Then we can think of the number pattern. And notice this only has 2 terms. You're missing the linear terms. If you want to write this 0b in its place, you're welcome to do that. But we're going to think about what times what gives us negative 25 and what plus what gives us 0. So we need the same amount, 1 positive and 1 negative, and we know 5 and negative 5 would make that happen. We can write it with our four terms, look it into pairs, and divide out what they have in common. The first pair we could divide out of b. The second pair we could divide out of 5. So we'd have b times b minus 5 plus 5 times b minus 5. Both pairs are being multiplied by b minus 5, so that's a common factor, and the other one would be b plus 5. Again, remember we said when we have two terms like that are being subtracted, this is what we call a difference of squares. For number 6, again, we look to see if it has a greatest common factor. In this case, it's 1, so we go to the second step, thinking what times what gives us 16, and what plus what gives us negative 10. We know that we could use a negative 8 and a negative 2 to make that happen, so we could write it as four terms, look it into pairs, and divide out what they have in common. First pair we could divide out an x, and the second pair we could divide out a negative 2. So we'd have x times x minus 8 minus 2 times x minus 8. Here's how both pairs have the factor of x minus 8, and the other factor results in the x minus 2. We've now factored 6 polynomials, and so we want to see, do you notice any patterns that exist? Perhaps you notice that the only greatest common factor we were working with here was 1, so the leading coefficient was for all of the patterns. And then as we do the second step, thinking of the product and the sum, you notice hopefully that the numbers that we're using for the patterns for the product, what times what, and the sum, what plus what, ended up being the factors to your polynomial. So for some of these, when the coefficient is 1, you may be able to skip some of the innermost steps to write your polynomial in factored form. So let's look back at the last example to show you what I'm talking about. So here we had x squared minus 10x plus 16, and we said the numbers we needed for the product were negative 8 and 2, as well as the sum, negative 8 and 2. Well, notice how by going through the process of factoring, those values showed up as your final factors. Here we have the x minus 8, here we have the x minus 2. Similarly with number 5, again we said the two numbers we needed for the product and the sum were negative 5 and 5, and notice how those, after going through the factoring process, ended up being your factors, b minus 5 and b plus 5. So perhaps you can shorten the factoring process. There is nothing wrong with writing it out as four terms, factoring into the groups to get those, but now hopefully we can see some patterns to simplify some steps. So when that leading coefficient is 1, perhaps you now can go from the standard form to the factored form a little bit more quickly. Let's see if we can condense that process with a couple more examples. So let's see if we can factor these trinomials. So again, we look to see does it have a common factor. In this case, it's 1, so we can think about the number patterns. What times what will give us negative 48, and what plus what will give us 8? Well, to make both of those true, I could use a positive 12 and a negative 4. That would make the product true and the sum true. So again, what we used to do is write it out with four terms, c squared plus 12c minus 4c minus 48. Break them into pairs, divide out your common factors. But again, because that leading coefficient is 1, we could simplify that process, hopefully, in saying, all right, well, if these are the two numbers for the product and the sum, one factor should be c minus 4, and the other factor should be c plus 12. And to check, remember, distribute your factors to get to the original polynomial. So let's check. C times c, that's c squared. C times negative 4, that's negative 4c. 12 times c, that's 12c. A positive 12c and a negative 4c gives you back the 8c. 12 times negative 4 is negative 48. So we factored the polynomial correctly with a lot less steps than we did before. Let's take a look at your next polynomial. D squared plus 4d minus 32. Again, the greatest common factor is 1, so we can think of the number patterns. What times what gives us negative 32, and what plus what gives us 4? We know that an 8 and a 4 would make this work as long as the 8 is positive and the 4 is negative. Again, because that leading coefficient is 1, we could simplify the process where we don't have to write out the 4 terms. You can if you need to, there's nothing wrong with that. But we should see the pattern that one of the factors would be d plus 8 and the other would be d minus 4. Again, to check, distribute. D times d, that's d squared. D times negative 4, that's negative 4d. 8 times d, that's positive 8d. Well, the positive 8d and the negative 4d brings you back to your positive 4d. And 8 times negative 4 is negative 32. So you factored it correctly. Let's try these. Can you factor your trinomials? So again, the greatest common factor is 1. The leading coefficient is 1. So we can think of our number pattern. What times what is 16, and what plus what is 8? I know 2 4s would make that happen. So one of my factors would be x plus 4. The other factor would be x plus 4. But notice, both of those factors are the same. So another way that we could write the polynomial in factored form would be the quantity x plus 4 squared. Again, this is what we call a perfect square trinomial for the original polynomial, and it comes from a perfect square binomial. For g squared minus 49, again, the greatest common factor is 1, so we can think about our number pattern. What times what gives us negative 49, and what plus what gives us 0, because that linear term is missing. So thinking about both of these rules, in order to add to get 0, one of them would have to be positive, one would have to be negative of the same amount. So I'm going to use a positive 7 and a negative 7 to make that happen. So again, that leading coefficient was 1, so we could write our factors as g plus 7 times g minus 7. Remember, we called this a difference of squares for the polynomial because that middle term is 0. While we've been doing all this factoring, let's see how we can apply it to real-world situations. So here we have a zoo exhibit where the zoo is building a walkway along two sides of the exhibit. The exhibit is rectangular with a width of 400 feet and a length of 200 feet. The walkway will have the same width on each side of the exhibit. We want to write a polynomial that will represent the combined area of the exhibit and the walkway. Well, again, here's the exhibit dimensions, 400 feet and 200 feet. We have to have the same amount of walkway on either side of the exhibit. If they want us to write a polynomial that represents the combined area of the exhibit and walkway, we actually want to find the area of this entire figure. So a couple of things that we have to remember is what kind of figure is it? It's a rectangle, and the area of the rectangle comes from the base times the height, or perhaps you've also referred to it as the length times the width. Well, if we think about the entire base, the length, that extends from this corner to this corner. So that would be x and 400, x plus 400 mathematically. The height, again, extends from here to here. So again, what is that represented by? X and 200. So mathematically, x plus 200. Well, that's the factored form for our polynomial. We want the polynomial form. So what we have to do is actually multiply those items together. So we're going to distribute like we've done in the past. So we take x times x times 400, 200 times x, 200 times 400 to see what results. And we end up with this. Notice again, you have some like terms that you can combine. So we could have x squared plus 600x plus 80,000. Last but not least, because we're talking about an area, you want to think about the units. And here they're specified, we're talking in feet. We're talking about area though, and that's a space. That's 2 dimensions. We want to make sure that we're saying we're referring to feet squared in our results. So now we have the polynomial that represents the combined area of the exhibit and the walkway. Let's take a look at another example. Here we have a large picture that was cropped to create a smaller picture, shown at the right. We want to write a polynomial that represents the area of the cropped photo. And here is the cropped photo that we're trying to represent. So again, what do we know about the problem? We have the figure for the photo, right? So here we have the original one. Let's think about the dimensions. We have something that's rectangular in shape. So again, the area would be the base times the height. Now as we look, the base here and the height here are the same, so this appears to be a special type of rectangle. When the sides are the same, it would be referred to as a square. But we're not using the entire figure, we're only using this corner of it. So let's think about how it changed. We've got a reduction in size. So instead of now the base being x, it's 5 units less than it was before. So we could represent this side length or this side length by an expression of x taking away the 5 inches, so x minus 5. The height again, we've reduced that in size. It was originally x, but now we've taken away 6 inches. So if mathematically, we could represent that by x minus 6. Again, we talked about the area being the base times the height. So we're going to multiply those two dimensions together to see what that will represent. So again, thinking about our rules for distribution. Everything from the first has to get distributed to the second. So x times x times negative 6. Negative 5 times x, negative 5 times negative 6. And we'll see if we can combine any like terms. You can see here that we have some linear terms we can put together. So we could have x squared minus 11x plus 30. Last but not least, ask yourself about the units. We're talking about inches here, and since it's a space that we're working with that's 2 dimensions, we have to talk about square inches in our results. So at this point, it's your turn to practice doing some more factoring of your polynomials and some applications with them by using your Unit 6, Day 9, that should be a 9 there, worksheet.